there's going to be 4 of us today, I think.
5 of us.
5. Of course, 5. All right. I don't know if anyone saw my notice yesterday. You did?
Yeah.
Okay, no, it's all right. You don't need to see it because you're here. Basically, just to explain, for those that are at home, I'm filming this and streaming it live on YouTube. So I told everyone that if they go on, they can see during our normal class time, which is now. I see we have a viewer. Who is that? Is that one of my physics students? Can you type something in the live chat, please, to see if it's you? Yeah, you should have got it as an email.
Yeah.
All right, so the people that are watching me at the moment, I can see there's 2 of you. Can you type something in the live chat so I can see who it is that's joined us? I want to know if it's our physics class. No, you guys don't need to see it. You're here in class. Okay. All right. Can you guys take out, please, your Starla books? We're going to be doing questions for this one today. Problem set 6, yes. Who's here? Melina. Hello, Melina. Welcome to the class. All right, we're working on questions from problem set 6 today from the Starla book. So take out your books, everyone. I'm just going to run and grab my whiteboard.
Yeah. Is she gone?
Okay, do we have anyone else? We've got Talia, we've got Melina. Brilliant. Okay, that means 1, 2, 3, we've got 5 altogether. You said Marcus is here. Oh, is that his bag? Oh, but he was. Well, maybe we'll rock up. He is here?
Yeah, he is.
Marcus! Come in. Nah, all right. We've got Melina and Talia, and we've got Prachi and Babita and Chogyal and apparently Marcus as well. And Paranith is with us as well. Okay, brilliant. So we've got a few of us. Okay, let's get started. I want to work on some questions from problem set 6 today. Before we do that, let's just remind ourselves of some of the stuff that we did yesterday. So we're talking about half-life. Now, just for those of you that are at home, can you just let me know, when I write on the board, can you see it? Type something in the chat to let me know if you can see the words that I'm writing on the board. Yeah, they can see it. Okay, brilliant. And is it backwards or can you see it the right way around? Tanya says, kinda, not really. Okay, I'm going to do my best to write on the board in a way that you'll be able to see. Let me know if there's anything that you like really can't see, and I'll explain it. Which one's that? Okay, so let's just go over quickly what we did yesterday. For those of you watching at home, some of this might be new stuff. If you didn't do the reading in the program from the textbook. Okay, so we're talking about half-life. Chogyal, define half-life for me, please.
It's the time taken for 50% of a sample to decay, 50% of nuclei in the sample.
Good. Time for 50% of the nuclei in a sample to decay. Exactly. Okay. And there were a couple of equations that we went through yesterday. So that's what half-life is. Before we get to the equations, people at home, can you see the words I'm writing on the board? Someone just commented, I'm not even in this class and I don't know who they are. But you're welcome to stay anyway, whoever just wrote that, and learn about physics. But yeah, okay. So that's half-life. That's our definition of half-life. Babita, can you tell me, please, what is activity?
Like, could you just the number of oxygen per second?
Number of decays per second. Excellent. Number of decays per second. And we have a special unit for that. We don't just call it decays per second. Prachi, what's my units for activity? Becquerels with a capital B and a lowercase q. Exactly, becquerels. Okay. Okay, they can't really see what I'm writing. That's a bit annoying. But okay, well, when we start doing some questions, people at home, I'm going to get you to do these questions. People at home, so Talia, Paranitha, and Melina, do you guys have your books on you? The Stala book? Please let me know in the chat if you don't have your Stala book on you, because that's what, yes, okay, a couple of you do, brilliant. Okay, let's go through the formulas that we did yesterday. So we had one formula for, let's write this in a different color, to calculate. So to calculate the number of nuclei left in a sample, the number of original nuclei left, I had this equation. Rabita, capital N means?
Number of original nuclei.
Number of original nuclei left. Prachi, N naught means?
The original number of nuclei.
Original number of nuclei. Good. Starting number or initial number. And then it's multiplied by a half to the power of little n, where I show you how little n is.
Number of half-life.
Good. Number of half-lives. And how would I calculate the number of half-lives if I didn't know it?
Time divided by the half-life.
Time divided by the half-life. And I write that T with a little half at the bottom to mean half-life. Yep. Okay. Nathan's with us as well. Yes, Nathan. Activity means number of decays per second, and it's measured in becquerels. Brilliant. Okay, so everyone that's at home, feel free to ask questions in the chat if there's something that you don't understand. I know that most of you guys weren't here yesterday when we went through this, so this is a brief overview. We're going to start doing some questions in a second. Let me know if you're at home and you have questions. Just post them in the chat. Okay, so that's how I calculate the number of original nuclei left. I also have a way of calculating the activity. What's my formula to calculate delta n over t? What's delta n here, Prachi?
The number of decays. The change.
The change in number of decays, exactly. Well, no, so close. It's the number of decays, right? The reason why this together, delta n, is the number of decays is because delta means change in, as you just said, and capital N is my number of nuclei that I have left, right? So the change in the number of nuclei I have left would be the number of decays. Yeah, Paranitha, capital N is the number of original nuclei left. So when I have a sample of radioactive material, those atoms, those nuclei are going to undergo radioactive decay. And when they undergo that decay, they'll change into a different nucleus. They'll change into something else. So the capital N is the number of the original nuclei that I have left. Once half of those original nuclei have decayed, the amount of time that takes is called the half-life. And yeah, let me know if there's anything else on the board that we've gone through that you didn't understand. Okay. Small n, no. Okay, Nathan, small n is not half-life. Small n here is the number of half-lives. Half-life, we write with a small t subscript half like that. That's how we say half-life. Small n is the number of half-lives. And we calculate the number of half-lives by doing the total time that has passed divided by the time in one half-life. We'll do some practice questions in a second to make sure that this is clear to everyone. We have one last formula. These first two formulas are both on your data sheet, right? So we didn't need to memorize them. They're on your formula sheet. The last formula we went through yesterday is the one that is not on your formula sheet, and it's the one that combines this one and this one. So we have exactly the same as we could do n equals n naught times a half to the power of 10 to calculate the number of original nuclei left. We can also calculate the current activity of a sample. And it looks exactly the same as this formula, but instead of n, we use a for activity. So a equals a naught times a half to the power of, and instead of writing that little n, I'll just write it in full t, the time divided by the half-life. Okay, no one at home has any questions. Cool. So those were the three formulas that we went through yesterday. This last one is the most important one to remember because it's the one that is not on your data sheet. Questions? No? Questions at home? All right, let's do some practice questions then. So take out your Star book, open up to problem set 6, please. Let's go through one or two questions all together, shall we? All right. Nathan says, what does the last thing say? Sorry, I'll move out of the way. So the last thing is the third formula we have is the more important one because it's the one that's not on your formula sheet. And that's a formula to calculate the current activity of a sample. And the formula for that is the same as the one for number of original nuclei left, but instead of n, instead of number of nuclei, it's activity. So a equals a naught times a half to the power of t. This is t for time divided by little t subscript a half, which is the half-life. What does Nathan say? The calculation is blurry. The calculation, you mean the formula? Seems like the blue is a bit better than the black on the screen. So let's just write that last formula again, big and in the middle, just to make sure that everyone's got it. And then we'll do some practice questions. Okay, so the main formula that I'm going to be using is the one for activity. A equals a naught times a half to the power of capital T divided by the half-life. That's my formula for calculating activity. Talia, okay, great question. Doesn't matter if the time is in seconds or hours. We spoke about this yesterday. What did we say? Exactly. It's whatever the half-life is in. Because this thing here, the only reason why we're doing that, t divided by the half-life, time divided by the half-life, the only reason why we're doing that is to calculate the number of half-lives. Together, that's meant to give us little n, which is the number of half-lives. So if my half-life is 3 seconds, let's say, then I need my time to be in seconds as well, because they need to be consistent. But if my half-life is, let's say, 1,000 years, then I need to do years divided by years to get the number of half-lives. I hope that answers your question. Okay, let's do a couple of questions from problem set 6. Did anyone start this at home yet last night? No? Okay. We'll do the first couple of questions all together, and then I might end the live stream and everyone can spend the rest of the lesson doing the questions themselves. So let's start with question 6.1. We're going to pull out the important information, as we always do from these questions, as we read. So, Chogyal, a radioactive counter shows that the rate of emission of beta particles from a radioactive source decreased to half the initial rate in 22 hours. So what do I know already? Time was 22 hours. And what happened in those 22 hours? Good. So what, question A there, what is the half-life of the element? No, what happened in the 22 hours? Decreased by how much? Decreased by half. So what's the definition of half-life? Good. Or in terms of activity, the half-life is the amount of time it takes activity to do what? To halve. So if the radioactive counter shows that the activity has decreased to half the initial rate in 22 hours, and what's the half-life? 22 hours, exactly. The half-life is equal to 22 hours, because that's how long it took the activity to halve. Is everyone cool with that? The page number, Paranitha, is page 64. Yeah, thanks, Talia, for helping her out with that. Okay, question B. What fraction of the original number of radioactive atoms is still unchanged in that time? How many? Half, exactly. A fraction would be a half. Half of them are still unchanged, half of them have decayed, because that is the definition of a half-life. Okay, question C is now extending that. So this is all the beginning easy stuff, just using the definitions that we know. Question C, what fraction of the original number of atoms will have disintegrated in 44 hours? So what do we know now? What's our time? What's our time in question C? 44 hours. The half-life is 22 hours. Good. We want to know what fraction of the original number of atoms will have disintegrated in 44 hours. So let's think about it as, if we have a timeline, starting at 0, after 22 hours, what fraction is left? A half. After 44 hours, how many half-lives is that now? How many half-lives is it? 2 half-lives. So this is a second half-life. So this will now get cut in half. So what do we have? 1/4, exactly. So by the time we reach 44 hours, 1/4 of our original sample is left. But that's not the question. The question is, what fraction of the original number of atoms will have disintegrated in 44 hours? So 3/4, exactly. 1/4 of it is left, which means that 3/4 has disintegrated. Is that clear? Okay, good. People at home are writing in their answers as well. Good, keep that up. Okay, we're going to skip question 2 for now, because we'll get to it maybe when we can do more. It's going to be a bit hard for the people at home to follow along with question 2, because I would need to draw the graph. Let's skip to question 3. One product of nuclear power plants is the isotope cesium-137, which has a half-life of 30 years. How many years will it take for the activity of a sample of cesium-137 to reduce to 1/16th of its original value? Okay, so what information do we know, Babita? We know the time. Good. What's the time? Well, do we know the time? We don't know the time. We know the half-life. Good. What's the half-life? 30 years. Excellent. What else do we know? Good. What's that? 1/16. Good. So the number of original nuclei atoms, it's not actually the number, this is like as a fraction, right? Is going to be 1/16 of what? Of the original amount, right? 1/16 of the original number of nuclei. Yeah? Good. And what are we looking for? We're looking for the time taken. We're looking for the number of years. Exactly. Okay, so we can use the formula here, and I'll show you like how to use the formula in a second. But most importantly is understanding what's going on here. So let's think about that timeline again. So if my timeline is now a number of years, at 0 years, I had the fraction 1. I had 100% of my cesium-137 nuclei. Yeah? How long's the half-life? 30 years. So after 30 years, how many do I have left? Half. After 60 years, I have 1/4. What should I write next here, Prachi? 1/8. Good. And how long will it take to get to 1/8? 90 years. Exactly. Because after that next half-life of 30, it's halved again. Next, 1/20 gets me to 1/16. Exactly. So people at home, Talia, good job. And Nathan, both of you, 120 years. Exactly. Good on ya. So it would take 120 years to get to 1/16 of the original amount. Is that clear? I just want to show you really quickly how we could use the formula to work that out. Because if we had n equals n0 times half to the power of little n, right? So we know that n is 1/16 of our original amount. So we're going to say 1/16 is equal to a half to the power of n. Okay, because my n noughts are going to cancel. So you wouldn't use this method when you're actually answering the question. It's a lot easier to think about it in terms of the timeline, like I just did. But it's just useful to like see how this might work, right? So I need to think a half to the power of something equals 16. Now, those of you doing methods might know how to do that mathematically, algebraically, right? Using like logs and stuff. But you don't need to do that. You can just think through in your mind, 2 to the power of what equals 16? So 2, 4, 8, 16, 4, exactly. So n is equal to 4. So the number of half-lives is equal to 4. And each half-life was 30 years. So the total amount of time has to be equal to 30 times 4, which is 120 years. Does that make sense, how I've used the formula there? Cool. Okay, let's do a harder question. That stuff's all the easy stuff. So Nathan saying you're too good at this. Don't get too carried away. This is question 1 and question 3. That's all the easier stuff. Okay, let's skip a bit just to do one more example, and then I'll give you guys time to do more on your own. Talia, would we need to use the question? Would we need to use the formula in a test or exam? No. If you get that kind of question, like what we just did in question 3 in a test or exam, you don't need to show me that you're using the formula. It makes a lot more sense to do it the way that we did it with like the timeline. So you don't need to show me that you're using the formula. You just need to show me you're working. It just doesn't need to be the formula. So if you're doing it just with the timeline or whatever, show me what you've done. Or if you're using the formula, then show me what you've done. But no, for a lot of these, it will be easier to not use a formula for a lot of the easier questions. But when we get to the harder questions, we're going to need to use formulas because they're a bit harder to think about. So let's skip down to question 7. Question 6.7 on page 65. Everyone got it? Okay, Prachi, you're going to help me out with pulling out the important information here. A sample of processed waste from a nuclear reactor contains 1.00 by 10 to the 24 plutonium-239 atoms. The half-life of plutonium-239 is 2.41 by 10 to the 4 years. Okay, so what do I know? The half-life is?
2.4 by 10 to the 24
Units?
years.
Years. What else do I know? What do I know? Good. So what symbol do I use for that?
No, and not.
N naught. Good. And what's N naught? 1 by 10 to the 24, right? Okay, question A. How many plutonium-239 atoms will decay in the next 2.41 by 10 to the 4 years? No, that's not dividing by half. You haven't divided by half there. You've divided by 1 by 10 to the 12. Okay, but I can see what you're trying to do. You're trying to do the right thing. I can see the working you have done. Yeah, thanks for your input there, Nathan. Very useful. Okay, but good thinking. Tell me what your working was there. Tell me what your thinking was. Okay, so let's think about this a bit more systematically. So for question A, what's the time? 2.41 times 10 to the 4 years, right? So then what's the number of half-lives there? How many? What's the number of half-lives in that amount of time? And what will that give me? 1, exactly. So that's 1 half-life. Yeah? Why are you confused? Chogal, what's going on? What? Okay, n equals little n equals the time divided by the half-life, which is 2.41 by 10 to the 4 divided by 2.41 by 10 to the 4. So that's going to give me 1. There's been 1 half-life. Yeah? Everyone with me? Cool. There's been 1 half-life, and we now need to think how many of my original plutonium-239 atoms will have decayed in that time. So I'm going to use this formula. Yeah, you with me? So let's think about it before we do anything on the calculator, Babita. N here is equal to 1. So a half to the power of 1 is just, what's a half to the power of 1? No, it's not 1, it's a half, exactly, right? Power to the power of 1, it just stays the same. So what fraction of my original nuclei will be left? Half of them. It's been through 1 half-life. That's the definition of a half-life. It's the amount of time it takes for half of my nuclei to decay. So after that 1 half-life, then we don't even need to do this formula, because that's just the definition of a half-life. After 1 half-life, half of the original nuclei will have decayed. You look confused. You're confused with this? Okay, I'm going to explain that to you in 2 different ways. The first way is ignore the maths. The definition of a half-life that we went through yesterday is that it's the amount of time it takes for 50% or half of the nuclei in a sample to decay. So if it's been through 1 half-life, then how many of the nuclei in the sample will have decayed? A half of them, right, exactly. Okay, so the amount left will be half of the amount I started with. Yeah? The other way I can explain that to you is mathematically, that's my formula, right? It's to the power of little n, which in this case we worked out equals 1. And anything to the power of 1 is just itself. So that's just half. Does that clear things up a little bit? Okay. So, yes, Talia, exactly. So, after that amount of time, which is 1 half-life, what do I put into my calculator to work out the number of things that have decayed? Exactly. 1 by 10 to the 24 divided by 2. Now, Chogyal, I think that's what you were trying to do before when you said 1 by 10 to the 12. Right, but that's not dividing it by 2. What do you get when you divide that by 2? Exactly. Yeah? Chogyal, what you did is like this, right? You took something that had a 1 and then 24 zeros afterwards, and you divided it by 2 to get something that has a 1 and half the number of zeros after it. But that's not how dividing by 2 works, yeah? Cool. Okay, everyone at home, did you follow that question? Question A? Let me know if you have any questions about it. Okay, we may as well do question B while we're on this. Question B, you'll need your periodic tables for. Question 6.7b is write an equation for the alpha decay of So tell me what I'm going to do. Tell me what I'm going to do. First step for me. Wait, first step. I need to write a whole equation. So what's going to go over here? PU.
And on the top, 239.
239.
And on the bottom is 94.
94. Good. What element is that, Babita? Plutonium. Excellent. Babita, you're going to help me with this next bit. What do I put next? Yes, Talia, it's 5 by 10 to the 23. What do I put? Uranium. What goes here?
235.
And here?
92.
Good. And Prachi, what else do I need? A helium nucleus. Exactly. That would be an equation for the alpha decay of plutonium-239 to uranium-235. Okay. Questions? Everyone happy? Everyone at home happy? Nathan says, easy. Good. Well, we haven't done any of the really tough questions yet, Nathan, so I'm glad that you think that. We're going to spend the rest of the lesson today working on problem set 6. Now, just before everyone at home logs off and works on those questions themselves, what we're going to be doing going forward is this. It said on the program that today we were supposed to be researching the applications of radiation, like traces and radioactive, radiocarbon dating, and other appliances like smoke detectors and things like that. We're going to do that tomorrow instead, because on the program tomorrow we're meant to be doing a mid-topic quiz that I would then mark and give back to you. I reckon with 3 of us in class, it's probably not much point doing the mid-topic quiz. I will still give you the questions to practice on your own, but we're not going to do it as a quiz in class. So we'll do the applications of radiation tomorrow, and today we're just going to work on problem set 6 to do all the questions to do with half-life. Everyone that's at home, I hope that was helpful. If you have any feedback, like things that I should be doing to make this more helpful, or if it wasn't helpful at all and so I shouldn't waste my time with it, please let me know, and do problem set 6 now. Let me know if you have any problems with it, all right? See you later. People at home, goodbye.